So welcome students. Today we're going to talk about, today's lesson is going to be about motion. It is the very first part of the Physics 11 course. It is a unit called kinematics, and it's all to do with how things move, be it cheetahs, ballet dancers, cars, buses. How do those things actually move? The learning objectives are we're going to distinguish between distance and displacement and between speed and velocity. And we're going to have an introduction to motion graphs, which we will talk about in more detail and do some activities in class. And so these are our learning goals. Now, before we talk about motion, we must say that everything is always in motion. One of the fundamental laws of physics in the world around us is that we're always moving. So relative motion depends on your point of view. An object is in motion if its distance from a reference point is changing. So my question to you would be, stand perfectly still, and are you in motion? So when you're standing perfectly still, are you in motion? Well, that depends on the point of view. From your point of view, no. But if you were viewed from space, you'd be moving at about 1,000 miles per hour with the rotation of the Earth. If you wanted to extend that and talk about the revolution of the Earth around the Sun, then we're moving in the orders of 50 to 100,000 miles per hour. So you can see that we are moving, but when we look at each other across a class and we're both sitting down, then relative to our point of view, no, we would not. So there's, as an introduction, there's two things I want to talk about. There's scalar versus vector. There are two different ways of talking about values. A scalar quantity is a quantity that has a magnitude only. So that means only numbers. So we're going to see a scalar quantity will have a number. So a scalar quantity we might talk about is 7 seconds. Okay, we just have the number, we don't have anything else, we have the number in the unit. A vector quantity has a magnitude and direction, and for a variable representing a vector quantity, an arrow is placed above the symbol. So you can see the example on the board of V, and it's got the arrow above it. This is for velocity. And there are certain times when we would need to know, are we going south, are we going east, are we going west, are we going north, and so on. And it can be useful. So if I asked you to place the following variables in the correct column, I'll do the first couple and then ask yourself, would you be able to do the rest? So time is a scalar quantity. It does not have a direction, so we can move that into the scalar. We already talked about the fact that velocity can be moved into the vector quantity. And mass does not have a direction, so it can be put into the scalar area. Hopefully by the end of next week we'll be able to, and by the end of this class too, explain the difference between weight, distance, speed, and displacement in terms of scalar and vector. Some have a direction, some do not. If they have a direction, they're vector. If they have no direction, they're scalar. First one that we look at is distance. When we talk about motion, we need to talk about distance. Distance describes how far an object has moved. The SI, or scientific unit of length, is the meter, not the kilometer, not the centimeter, the meter. The distance, you'll notice, is just describing how far an object has moved. We don't care about direction, therefore distance is a scalar quantity. So distance is scalar because there is no direction. So it's a scalar quantity. And displacement, on the other hand, is the distance and direction of an object's change in position from a starting point. So if we look at this schematic, and we talk about students starting from school at lunchtime maybe, and they go on this sort of wondrous trail over here. Student A goes this way, and maybe student B takes the direct route, okay, straight through Felsted Park. They will both end up at Danforth shop. However, they'll have different distances. The distance for the first one, so the distance for A will be much greater than the distance for B. because it's just the amount traveled. However, their displacement would be the same because they end up the same distance. They end up the same amount from the starting position. So remember, displacement is the distance and direction from the starting position. So for both of them, they ended up in the same place. They have the same displacement, but a different distance. Okay, you'll also see the other schematic at the bottom, which you can look at on the side rather. So we talked about unit distance and displacement. What about speed? Speed is the distance an object travels per unit time. So it is that distance over time. Again, we're talking purely in scalar quantities here, and you may have done speed calculations before. So a car traveling at a constant speed covers a distance of 750 meters in 25 seconds. What is the speed? Well, it's just simply a case of figuring it out. 750 meters, which is the distance, over 25 seconds, which is the time. And then that's going to give you a figure of 30 meters per second. Okay, make sure that you have those units in there. The unit of speed would be meters per second. You'll notice it doesn't have a direction. It is scalar. And what we looked at was the average speed. So we don't know whether there was, whether there was accelerations within that, but it was just the average speed. The instantaneous speed is the speed at exact time. So when something is speeding up or slowing down, its instantaneous speed is changing, just like the diagram on the right here. So in order to get the instantaneous speed, you would get what's called the tangent line on a graph which is looking at the distance against time. So what we normally look at is average speed. Now, in physics, we tend to talk more about velocity. Velocity is the speed of an object and direction of its motion. Direction is very important here. An object with a uniform velocity means that its velocity does not change. When you guys are sporting those lovely uniforms Monday to Friday, a uniform basically means that everything is the same. The uniforms all look the same, and a uniform velocity does not change. It means the velocity would be the same. So if we take this lovely armadillo over time and we step it through, the velocity would not be changing. It is not speeding up, as you can see on the screen. It is not changing. So if we move the armadillo back to here and we work it through, if the armadillo was able to lay an armadillo egg, if they could, every second, you would see that the distance every second it would be dropped at the same point. So the distance between them, every second, if it drops, if an armadillo could lay an egg, and that would be wonderful. If it was going at a uniform velocity, this distance, let's call it d1, would be equal to this distance here, d2. The distance between those drops. It is not speeding up, and this is what's referred to, what we're looking at here with the dots is what's referred to as a motion diagram. You can see that the dots are nicely placed, and this is for a uniform velocity. So there's no acceleration, the velocity is changing, covering the same distance every second. On a motion graph, if we look at distance covered against time, we would see that it's going the same distance against time. So every second it's going the same amount of distance. So for 1 second, 2 seconds, 3 seconds, it's covering the same distance, right? So when we're looking at these things, we would expect to see the same value for slope. In other words, that velocity is not changing. The distance covered per time is not changing. Now, what if the velocity is in fact changing? So our armadillo is changing, and our armadillo is actually speeding up. So it starts slow, and then it starts to speed up. Well, in that case, the armadillo is going to cover more distance as the seconds progress. So in this case, what we'll see is that D2 is now greater than D1 on the motion graph, because the armadillo is speeding up. And that is a velocity change. And in fact, the armadillo is covering more space, is covering more distance as the seconds progress. So it might go, you might see it on a graph something like that. Okay, this is a case where the armadillo is speeding up. The velocity is not uniform. That is what's referred to as acceleration. It's the rate of change of velocity. And like velocity, it's dependent on direction. So we've got, it is meters per second per second. So it's the rate of change of velocity every second. So it's your meters per second for velocity divided by second again. And the unit for that is sometimes shown as meters per second squared. Not meters per second, meters per second squared. If we look at the cheetah, similarly, let's do an example of a cheetah slowing down towards a kill. The cheetah is going really fast and then slows down. If the cheetah was able to drop some cheetah spots, we would see if it was able to do it every second, we would see maybe it's covered this distance the first second, and the second second it would cover less distance. The third second, even less and less, and so on. And you can see from the motion diagram that it is slowing down. So in this case, we've got D1 and we've got D2. And D1 is greater than D2. More of a distance covered in D1. And if we were to show that on a motion graph rather than a motion diagram, you would see it's covering a large distance and then tapering off. Okay, so this is an example of something that is the acceleration. It's actually slowing down. We sometimes call it deceleration. Another way to look at it is negative acceleration. So we're going to move on in class. We'll talk about looking at motion graphs. I've introduced you to two. Just an introduction. We talked about position graphs, position time graphs, and we talked about velocity time graphs. Now we will look at different scenarios for each one of those. And we will build up to looking at a distance time graph like we have here. You can see various things. Hopefully you can see that in the first segment from seconds 1 to 4, there is a constant velocity, uniform velocity. From 4 to 7, the object is not actually moving. The distance is not changing. So the object is stopped. And from 7 to 10, there is a constant velocity again, no acceleration. The slope will tell you the velocity, so the steeper the slope, the higher the velocity. So that's an introduction to terminology in this unit. We've talked about distance, displacement, velocity, speed, and we've also introduced how we would show those. Show that motion. One way is to use numbers and equations. The other way is to use a motion time graph. And we've talked today about position time graph and velocity time graph. So hopefully you have a better idea of those concepts, and we will discuss further in class tomorrow. See you then.